see what's going on, and that's when I pulled out my camera and I noticed there was a gentleman on top of the power lines.
A man with a death wish had climbed on top of the wires and was quite literally flirting with death.
I thought as soon as he started climbing across 2 lines, he was going to get electrocuted immediately.
Helpless police stood by as the man resisted arrest. Finally, the inevitable happened.
The sound that I heard when he touched the power line was just incredible. It just sounded like a humongous buzz, like if there was millions of bees, and then I just saw what I saw on the camera. I didn't feel anything, it was just a shock.
Looking through the viewfinder was one thing. The human dimension of what Tommy had witnessed began to sink in.
I just heard people scream, oh no. Some women were just moaning like they were going to faint. See what's going on, and that's when I pulled up.
All right, so there are a couple of things here that we need to focus on. This kid is right. He's not getting electrocuted. That's surprised a lot of people. Why is it that he's not getting electrocuted? A lot of you guys are thinking, oh, I know why, because he's wearing shoes. I don't like the rubber shoes. Oh, yeah? If that's the case, how do you explain the fact that his back is touching these wires? All right? How come he's not getting zapped? Obviously, I know that these are live wires because these guys are keeping a safe distance because they don't want to get electrocuted. And then he's going to get zapped only when he goes across that little thing that you're looking at, which is known as a transformer. His life is about to be transformed. I don't know what he does. He touches something here, and there's a huge potential difference, the voltage difference, and that's when he gets zapped. All right, in slow motion, you notice that the body heats up immediately. It starts to glow. And then he goes down. All right, so the question is, dead or alive? A lot of people will say, yeah, he's dead, definitely. You can almost see his soul just getting up and looking around, right? There's the proof that there's life after death, in essence. Well, believe it or not, guys, this guy survived. All right, so how do you survive something like that? It's exactly the same thing that happened to the other guy. Ended up losing his arms, remember? Because his bone marrow got fried. It's just a flash injury. Well, this guy, as this all happens, had no recollection of how he got on top of these wires. He was high on something illegal, and next thing you know, he's in a hospital. He's got burn injuries, obviously quite a few broken bones. I think he might have been in a coma for a while, and that's the extent of it. He did survive. All right, so the question is, what is a transformer? I'm not talking about the movie. I'm talking about the actual transformer. All right, so the transformer is, look at it right here. If you go across a transformer, you will get zapped. On top of that, just an interesting question. Why is it that he's not getting electrocuted? Why is it that he's not getting electrocuted? All right, he's touching the wires all over the place. All right, so this wire is obviously, he's not exposed, but these wires are. And he's not getting electrocuted for exactly the same reason as to why the birds don't get electrocuted. Not because the birds have tiny little birdie shoes. They don't get electrocuted, and that was a test question. And a lot of you guys did well on that test question, surprisingly. The reason why you don't get electrocuted, there are 2 reasons for it. And most of you guys, if he's got one of them right, the reason why this person is not going to get electrocuted is, number one, the current is going to be on the wire. The body offers a lot more resistance than the wire itself. So the body becomes parallel to the circuit, right? As a result, not much current is going to be going through the body. All right, so some of you guys got that, which is good. The other reason is, most of you guys said there's no voltage or potential difference on the wire, which is not correct. If there's no voltage or potential difference on the wire, and obviously there would be no current on the wire. There is voltage and potential difference on the wire, guys. It's not an equal potential surface. The voltage difference depends on your contact points, right? Remember that it's step potential? All right, that's what it is. The legs, contact points are fairly close to each other. Closer the contact points are, obviously, the smaller the potential difference is. So not much current. Even if there is current between the contact points, your body is already parallel to the wire itself. So which means that not much current is going to be going through your body regardless. All right, so that's the reason why the birds don't get electrocuted. That's the reason why this person was okay up until he decided to go across a transformer. All right, so he's going across the transformer. If there's a wire here, obviously there's going to be a voltage difference. I don't think he hit a wire. I think he got pretty close to the tree, branch of a tree, and then he got zapped. That's a bunch of questions for you guys. Who is the inventor of the radio? I'll wait until I know that. Nearly no one knows the answer. This is one of those odd things. All right, the inventor of the radio is this guy's Italian. His name is Marconi. He invented the radio, for which he also won the Nobel Prize. In 1903, physics Nobel Prize was awarded to this guy. His name is Marconi. X-ray machine, the guy who invented the X-ray machine, ended up winning the 1901 Nobel Prize, 1900 and 1901. The first Nobel Prize in history went to this guy. This guy's German. And then vacuum tube amplifier, DeForest from the United States, I think it's in the 20s. Fluorescent bulbs, neon lights, speedometer, prediction system for the cars, basics behind radar, electron microscope, microwave oven, and you will find different names under each and every single patent, despite the fact that the original patents are held by this guy. His name is Tesla, Nikola Tesla. The thing about Tesla is he should have won the Nobel Prize in physics at least 3 times. He won it absolutely no time at all. He didn't win the Nobel Prize at all. On top of that, despite the fact that he was fairly well known in the peak of his career, by the time he was old and about to die, he was almost forgotten. All right, so what happened to this guy? Why is it that he became forgotten? And then obviously his name got revived back up in 1970s, and today he's recognized to be as one of the geniuses that made the 20th century possible. All right, so the question is, how come he didn't win the Nobel Prize and some other people did for the inventions that this guy had?
On December 12, 1901, Italian inventor Guglielmo Marconi became the first person in history to send a message across the Atlantic Ocean through empty space. By using radio waves to carry the signal instead of wires, he helped start a revolution in the way we communicate.
So that's Marconi, the guy who won the 1903 Nobel Prize for inventing the radio. Physics 1 is all about Newton. Physics 2 is all about Faraday. Let's talk about Faraday.
In the early 19th century, scientists didn't think in terms of energy. They thought in terms of individual powers or forces. These were all disconnected, unrelated things. The power of the wind, the force of a door closing, the crack of lightning. The idea that there might be some sort of overarching, unifying energy which lay behind all these forces had yet to be revealed. One lowly man's drive to understand the hidden mysteries of nature would begin to change all that.
Young Michael Faraday hated his job. He was uneducated, the son of a blacksmith. He'd been lucky to become a bookbinder's apprentice. But Faraday craved one thing. He craved knowledge. He read every book that passed through his hands. He developed a passion for science. All of his free time and his meager wages were poured into his self-education. He was on the threshold of an incredible journey into the invisible world of energy.
Faraday had impressed one of his master's customers and was rewarded with a ticket that would change his life.
Excuse me, please. Can I pass, please? Can I pass? Some of us are trying to improve ourselves. If people will let us.
Of course. Pass.
This way to a better life.
In the early 1800s, science was a pursuit of gentlemen, something Faraday was clearly not. He had a rudimentary education. He'd read widely. He'd gone to public lectures. But in 1812, he was given tickets to hear Sir Humphrey Davy, the most prominent chemist of the age.
19th century scientists were the pop stars of their day. Their lectures were hugely popular. Tickets were hard to come by, and Davy reveled in his status.
They're waiting.
I knew. He was also a keen follower of the latest fashion, nitrous oxide or laughing gas. He said it had all the benefits of alcohol without the hangover.
Electricity, ladies and gentlemen, a mysterious force that can unravel the confusing mixture of intermingled substances that surround us and produce pure elements.
Davy was an absolutely first-rate scientist. However, many will come to say that his greatest discovery is Michael Faraday.
It was unknown, that is, until I isolated potassium from molten potash and sodium, as I showed you last time, from common salt. That same magical electricity.
Faraday may not have been born a gentleman, but he wasn't going to let class barriers stop him from pursuing a career in science. He worked for nights on end to bind his lecture notes into a book for his new hero.
Lord, help me to think only of others, to be of use to mankind. Help me be part of the great circle that is your work and love. Lord, I am your servant.
Well, this is excellent work, Faraday. So what is it you aim to do with your life?
My desire, sir, is to escape from trade, which I find vicious and selfish, and to become a servant of science, which I imagine makes its pursuers amiable and liberal.
Really? Well, I shall leave it to the experience of a few years to set you right on that score. Look, I haven't anything at the moment. I'll send a note if anything comes up.
Despite this humiliating setback, Faraday was determined to break free from his daily toil. His patience was rewarded.
Hero, meet Miss Michael Faraday. He's going to be my helper while I recover. He assures me he is a Christian fellow. Perhaps with God and Faraday in charge of chemicals, you and I will be safe in our place of work.
Thank you, Professor Davy. Welcome, Faraday.
Oh, no, thank you, and thank you, Sir Humphrey.
Just stick to your job and do as you're told, and you'll be fine, Faraday.
Faraday became the laboratory assistant, eagerly absorbing every scrap of knowledge that Davy deigned to impart. But in time, the pupil would surpass the master. The big excitement of the day was electricity.
Another charge, Newman.
The battery had just been invented and all manner of experiments were being done. But no one really understood what this strange force of electricity was.
The academic establishment at the time thought that electricity was, like a fluid flowing through a pipe, pushing its way along. But in 1821, a Danish researcher showed that when you passed an electrical current through a wire and placed a compass near it, it deflected the needle at right angles.
This was the first time researchers had seen electricity affect a magnet. The first glimpse of two forces which had previously been seen as entirely separate, now unified in some inexplicable way.
Faraday, come look at this. There's a bright spark around here, but you can work it out. Ersted's reported an amazing finding. We're just replicating it here.
Let's try the compass on the other side.
Now, that is remarkable.
But if the electrical force is flowing through the wire, why does the needle not move in the same direction, parallel to the wire?
Quite.
Let's try turning the whole apparatus round.
Again, Newman.
So, the electrical force goes this way, the compass points that way. How can one affect the other?
Perhaps the electricity is throwing out some invisible force as it moves along.
What?
Perhaps some sort of electrical force is emanating outwards from the wire.
Oh, my dear boy, let me tell you that at the University of Cambridge, electricity flows through a wire, not sideways to it.
Well, that may be what they teach at Cambridge, but it doesn't explain what's happening before our eyes.
No, let's just get on. Let's swap the compass to below the wire.
Why the compass was deflected at right angles, why the electricity was affecting the compass at all, dumbfounded Davy and many others.
As we celebrate the marriage of Michael and Sarah.
For Faraday, however, the problem became an obsession. It was a fascination inspired by his religion. For him, the problem was a way to understand God's hidden mysteries.
There was a small, almost persecuted group in London called the Sandemanians. They were religious, not really a sect, they were just a small subset, sort of like Quakers. Faraday was a member of that group. It was a very gentle, decent group. They believed that underneath the whole surface of reality, everything was created by God in a unified way, that if you opened up one little part of it, you could see how everything was connected.
Michael Faraday was someone who, like Einstein, thought in terms of pictures.
Faraday was different from anybody else. He had a flair for understanding his experiments, for understanding what was really going on inside them.
By methodically placing a compass all around an electrified wire, Faraday started to notice a pattern.
What everyone else at the time had been taught was that forces travel in straight lines. Faraday was different. Faraday imagined that invisible lines of force flowed around an electric wire. And then he imagined that a magnet had similar lines emerging from it, and that those lines get caught up in this flow. It was a bit like a flag in the wind.
But Faraday's great leap of imagination was to turn this experiment on its head. Instead of an electrified wire moving a compass needle, he wondered if he could get a static magnet to move a wire.
I've never seen you like this, Faraday. You look like a happy child.
I'm shaking, Newman. Underneath, I'm shaking. You see, John? You see?
Yes.
This is the experiment of the century. It's the invention of the electric motor. Scale up the magnets and the wires, make them really big, attach heavy weights to them, and they'll be dragged along. But almost more importantly, he's inventing a new kind of physics here.
Although he didn't realize it at the time, Faraday had also just demonstrated an overarching principle. The chemicals in the battery had been transformed into electricity in the wire, which had combined with the magnet to produce motion. Behind all these various forces, there was a common energy.
right, so Faraday, this guy had a real weird background. Had no formal education. He was a bookbinder by profession. His dad was a blacksmith, and then somehow this guy was a genius. He couldn't handle mathematics, and that's the reason why he did physics visually in his head. And that's the reason why the physics too is extremely visual. You got the electric field lines starting off the positive charges, ending on negative charges. You got the magnetic field lines just wrapping around, starting at the North Pole, ending on the South Pole. Everything is visual. Everything was visual for this guy. He helped shape electricity as well as magnetism, and that's the reason why everything that we've done up to this point is visual. And so that's his gift from us, for us in essence. Faraday also was the last physicist who could not do mathematics. Today, you cannot do physics without math. It's out of the question. All right, so year is 1819, and Ørsted, by chance, doing a physics lecture, discovers that the current causes the magnetism. So the magnetism is caused by the electricity, in essence. So the people were wondering at the time, the people who were working in physics, they were looking for some kind of a symmetry or pattern. They knew that the current causes magnetism, so they wanted to know if the opposite is also true. Can we generate currents using magnets? And Faraday came up with the answer roughly about 10 years later. Faraday discovered that, yeah, it is possible to generate current using magnets, except here's a catch.
A couple of months earlier, Davy had been elected president of the Royal Society, which was the elite body of English science. But then he saw this great discovery published in the Quarterly Journal of Science. I don't know if he was envious, but he certainly saw that this young man who had been his assistant, this mere blacksmith's son, had come up with one of the greatest discoveries of the Victorian era.
Davy accuses Faraday of plagiarizing similar work from another eminent British scientist, William Wollaston.
So, Faraday, what does Wollaston make of all this?
He's written to me and assures me that he's taken no offense. And he acknowledges that what I published was entirely my own work.
Right. Davy is just being an ass.
But will Davy now retract his allegation?
Sadly, no. In fact, he's still vehemently opposed to you being elected a member of the society.
Really? And what do you think?
Faraday, my dear boy, you have my vote.
Hang on. I believe you even have Wollaston's.
What a mess.
Well, no matter. It's the science that counts. So tell me, how does this wire of yours spin round its magnet? What mysterious forces are at play?
There seems to be an electromagnetic interaction. In my mind, I see a swirling array of lines of force spinning out of the electrified wire, like a spiraling web.
But invisible lines of force, it's all a bit vague, isn't it?
Faraday, might I have a word of prayer?
Certainly.
Listen, Faraday, let's stop this nonsense. I want you to take down a pile of paper from the notice board.
Sir Humphrey, I see no reason to take it down. My friends have proposed me. It is they who put the paper up. I will not take it down. Good day.
Faraday was elected to the Royal Society. Davy died 5 years later, a victim of his many gaseous inhalations. In time, Faraday's world of invisible forces would lead to a whole new understanding of energy. He'd started what Einstein would call the Great Revolution.
All right, so here's what Faraday discovered. Evidently, you can generate current using magnets, except there's a trick involved. What you need to do is when you have a wire, just turn it into a loop, and then just change the strength of the magnetic field inside the loop. That's it. All right, so this is what Faraday discovered. Yes, you can generate current by varying the strength of the magnetic field inside the loop of a wire. All right, so here's the magnet. It's not moving. That's the number of magnetic field lines being intercepted by this area of the loop. And then what you do is you move the magnet back and forth. All right, so you move the magnet towards the loop, away from the loop. All right, so when you move the magnet towards the loop, the current goes one way. And then when you pull the magnet away, the current is going to go in the opposite direction. That's it. Notice that the direction of the current is going to keep changing, right? So the direction of the current is alternating. This is known, hence the reason why this is known as the alternating. So what generates the current is the fact that you end up changing the strength of the magnetic field within the loop, inside the loop. All right, this is known as the Faraday's law. Any variation of the strength of the magnetic field inside the loop is going to generate current. Now, there are a couple of ways you can actually do that. Number one, you can change the strength of the magnetic field inside the loop, or you can have the area of the loop exposed to the magnetic field change. In essence, you're changing the size of the area exposed to the magnetic field. And one way of doing it is you can kind of spin the loop inside a constant magnetic field. Or you can move the loop
effect
back
can be
and forth.
seen in a simple loop of wire connected only to a meter which measures electric currents. If I move this conductor in the presence of the Earth's magnetic field, then that gives rise to currents. Once you have currents, those give rise to magnetic fields.
But the
All right, so this guy, he's got the loop, obviously, loop of wire. He's keep changing the orientation of it relative to the Earth's magnetic field. By varying the orientation of the loop, he's actually changing the area of the loop which is exposed to the magnetic field. So by varying the area of the loop exposed to the magnetic field, he's able to generate current. So that's how it is done. So there are two ways of doing it. All right, so we got the DC current and then the alternating current. DC current is something that we've been discussing so far. It's a direct current, which means that the direction of the current is constant. Current is going to be generated by a battery. All right, if you're using magnets to generate current, it's known as alternating current. So the current is generated by magnetism. So the direction of the current is alternating. All right, so you will get to see the sign for alternating current voltage supply. This is a power generator in essence. It wiggles up and down, which means that the current, the voltage goes up and down. When the voltage goes up and down, voltage is what drives current. So the current is going to also go up and down. All right, so there are two ways you can generate alternating current. One way is to vary the strength of the magnetic field inside this area. All right, so here's the area of the loop, delta B divided by delta T. Delta means change, so we are changing the strength of the magnetic field in time through the area of the loop. In return, so what happens is it's going to induce current. All right, so this statement is a statement of what I just described. If you vary the strength of the magnetic field through the area of the loop, area is constant. What's going to happen is it's going to induce current within the loop. That's one way of doing it. The second way of doing it is if you change the area of the loop, which is exposed to the magnetic field in time, inside a constant magnetic field. So magnetic field here is constant. We're just changing the area exposed to the magnetic field in time, in essence. All right, that's also going to induce current. All right, so varying the strength of the magnetic field inside the loop is going to induce current. And if you have the area exposed to the magnetic field change, it's also going to induce current. Of course, you can change the area exposed to the magnetic field by spinning the loop, in essence. Now, instead of making two statements regarding how you can induce current, it's better to come up with one single statement, which is going to be all-encompassing. So we can come up with a statement of flux one more time. Remember, flux, guys, flux means flow. In this case, what's flowing is the magnetism through the area, right? So this is flux is going to represent the amount of magnetism, which is going to be intercepted by the area of the loop, in essence. All right, so that's the amount of magnetism, which is going to be flowing through the area of the loop, in essence. All right, so we'll get to use that statement. All right, so if you vary the strength of the magnetic field within the loop, that's going to change the flux. Changing flux is going to induce current. Or if you keep the magnetic field constant, and within that constant magnetic field region, if you just change the area exposed to the magnetic field, maybe by spinning the loop within that region, once again, it's going to change flux. And changing flux is going to induce current. All right, so this is the essence of the Faraday's law. This is the essence of the Faraday's law. Simply put, changing flux will induce current. So any change in flux will induce current, which means that if you vary the strength of the magnetic field inside the loop, you got current. If you vary the area, size of the area exposed to the magnetic field, once again, it's going to induce current. So it means two things. All right, so the lecture review material, AC versus DC. DC is direct current, DC is alternating current. DC is something that you generate using a battery. Alternating current is something that you generate by using magnets, right, through the Faraday's law. All right, so we will just jump around at this point. I'm going to go up and down. All right, so what's flux? Flux means flow. In this case, the magnetic field is flowing through the area of the loop. That represents the amount of magnetic field intercepted by the area of the loop in essence. All right, so that's our flux. All right, so Faraday's law, simply put, change of flux is going to induce current. Any change in flux is going to induce current. If you vary the strength of the magnetic field inside this loop, it's going to change the flux, so that's going to induce current. What else? If you vary the area of the loop exposed to the magnetic field, that's also going to induce current. All right, so flux is the amount of magnetism intercepted by the area of the loop. Faraday's law says any variation of flux, any change in flux is going to induce current. The area of the loop exposed to the magnetic field, if you vary that, that's going to induce current. Okay, guys, D is the same as delta in essence. Okay, except it's the expression we're using calculus, which means indicates a small change. It's the same thing. So area exposed to magnetic field is changing in time. That's what it means. In essence, you're changing the flux that induces current. All right, in this case, you vary the amount of magnetic field intercepted by this area in time, so that's going to induce current. So the next question is, changing flux, will it induce voltage or does it induce current directly? All right, so what it does, in essence, changing flux is going to induce voltage. when you change the flux, what needs to happen? The charges need to experience a force. So change of flux needs to generate an electric field. The electric field acting on these charges will induce a force. As a result, the charges will move along the direction of the force. So which means that these charges will have energy stored in them, and because they're free to move, that energy is going to turn into kinetic energy of these charges, meaning that there's going to be current. So which means that the change in flux will induce voltage, and voltage is what drives current in essence. All right, so which one comes to first? Is it the chicken or the egg? That's the sort of stuff that we have. All right, in physics, the distinction is important. So what do we know? We know from the previous lecture that the current is going to be caused by a voltage potential difference. All right, so which means the charges will have to move on the direction of the electric field. All right, the electric field acting on the charges will induce a force on them and get them to move, which means that the energy is going to get transferred to the charges. So the energy stored within the electric field is the voltage. Voltage is what drives current in essence. So what that means is the change of flux is going to induce voltage, and voltage in turn is what drives current. All right, so the change of flux induces voltage, and voltage is what drives current. So any variation in flux is going to induce voltage or potential difference within the wire. And the voltage or potential difference in turn is what drives current. All right, now an adjustment to this formula is coming up. Instead of V, we're going to end up using this symbol epsilon. It's going to stand for electromotive force. Electromotive force is the same as voltage, except at the time of Faraday, they didn't know anything about voltage or whatever, so they thought that there was a force that was driving the current, so they called it the electromotive force. So traditionally, that's the term that we get to use. So V becomes epsilon. Epsilon stands for EMF. EMF means electromotive force. Electromotive force is the force that drives current in essence. All right, so the modern name is voltage. The traditional name is EMF, electromotive force. So what that means is any variation in flux is going to induce voltage, and voltage in turn is what drives current. There's N here that we will discuss, and there's also a negative sign here. That's going to require a little bit of discussion that we will have to focus on. So there's a negative sign. It's going to come from something called the Lenz's law, something that we will discuss today. Not necessarily now, but it's something that's going to get discussed today. All right. It's going to be related to the direction of the current. All right, let's focus on N. N represents the number of turns. So if you change the flux through one single loop, you will get a certain amount of current. If you double the number of loops, you're going to be changing the flux through both loops. As a result, you end up doubling the amount of current that you have. If you have 3 loops, current is going to be 3 times larger. If you have 10 loops, the current is going to be 10 times larger. So number of loops that you put in your wire is going to increase or decrease the amount of current that you have. So it's going to give you a control in terms of how much current you can get out of this system. So increase the number of turns, the voltage goes up, the current goes up. Reduce the number of turns, the voltage goes down, the current goes down. Increase the turns, voltage goes up, the current goes up. Reduce the turns, voltage goes down, the current goes down. All right, so now we have, not only do we know how to generate current, we can also control the amount of current that we want to generate, and that's what Faraday gave us. So Faraday's law, simply put, any variation within flux is going to generate, induces voltage. Voltage is what drives current. All right, so by increasing or changing the number of turns, you can increase the voltage, you can increase the current. By reducing the number of turns, you can reduce the voltage, and in turn, that's going to reduce current. All right, so increase the number of turns, voltage goes up, the current goes up. Reduce the number of turns, the voltage goes down, the current goes down. All right, negative sign is going to come from the Lenz's law, something that we will discuss
Deep in the heart of the Royal Institution, Faraday conducted experiments to understand how they were linked. In one experiment, a copper wire carrying electricity somehow provoked a nearby compass to move. In another, Faraday tried to do the opposite. Use a magnet to generate electricity.
Which led him to invent the electric generator, which is an example. We have a permanent magnet and a coil of wire.
So the wire is wrapped around the cylinder.
Wires wrapped around the cylinder, and you push and pull the magnet in and out of the cylinder to generate an electric current.
I like the lights. Where's the Christmas lights for?
Well, that's to show the electricity is passing.
Oh, okay.
Faraday did not use light-emitting diodes.
I think he should have done that. It's a great mistake.
And all electricity power stations throughout the world use this principle of generate electricity that Faraday discovered down here in 1830.
Faraday had generated electricity simply by moving a magnet through a coil. A discovery that would forever be associated with his name. But he was left with perplexing questions. There was no physical contact between the electric wire and the magnetic needle that moved, nor between the moving magnet and the copper coil. They were affecting each other through seemingly thin air. How could that be?
Now, what Faraday thought was happening was that there were lines of force coming out at the end of the magnet, which were then cutting the wire within the coil to move electricity around the coil.
The idea of mysterious lines coming out of the magnet to generate electricity may have seemed outlandish, but Faraday had a simple experiment that could prove their existence.
So he took a very powerful permanent magnet, placed some paper on it, sprinkled iron filings over it to represent the lines of force.
It never fails to impress that.
Of the magnet, and you can see the sort of three-dimensional
So these
structure.
are coming up here and swinging around, and then coming down into this point.
And Faraday sort of made permanent examples of this and sent them around to all his mates in Europe to show the space had structure as a very strong argument for his field theory.
So Faraday thought it was an invisible force field at work here.
Well, literally a field. That means Faraday still brings the word field into science, and it's invisible, as you say. But so this is why this is just a representation. It shows the existence of those invisible lines.
Faraday's iron filings experiment revealed the existence of an invisible field stretching out into thin air. These fields, he thought, were responsible for the experimental results he'd seen. Despite having physical proof, Faraday lacked a mathematical description of how the field was generated, or why it affected things around it. Without a mathematical proof, many 19th century scientists dismissed the theory as speculative.
We've been generating current ever since the 1880s the same way, guys. The technology moved on, obviously. We got Wi-Fi, we got cars, and we got cell phones. And we've been playing God for a while, but I got news for you. The electricity has been generated exactly the same way ever since the 1880s. What do we do in order to generate electricity? Literally, you have a loop, a wire, so coil, a wire, and then you spin it inside a constant magnetic field, 60 times per second. So what it does is going to give us an alternating current. The current is going to change direction 60 times per second, and that's it. That's it. Okay, so except this coil that you're looking at, it needs to be spun 60 times per second. 60 times per second. It needs to be done mechanically. You see a hand here. There's no way you can spin something 60 times per second on your own. No muscle power is going to be good enough for something like that. So how do we spin the coil mechanically? Obviously, it requires some kind of an advanced gear system. So you spin something once or twice per second, and through the gear system, it's going to speed up. And by the time you get to this level, it's going to be spinning 60 times per second. So that's what happens. But mechanically, how do we spin it? If you're dealing with hydroelectric power, what's happening is the running water is going to spin the turbine, the pedals that you got. Not turbine, it's a turbine. A turbine is something you wear. It's a turbine. All right. So you got the pedals. The turbine is going to start to spin once, I don't know, 10 times, 20 times per second. And then by the time you get to this level, that thing is going to spin 60 times per second. That's one way of doing it. You got the wind power, once again. It spins once, if you're lucky, a minute or twice a minute or something. And by the time you get down to this level, this thing is going to be spinning about 60 times per second. You got the nuclear power generators. You guys are thinking, oh my God, they're using nuclear bombs. Not really. Nuclear power generators work exactly the same way as the coal power generators. The only thing you have to do is just boil water. All right, so when you boil water, it turns into steam. You turn it into pressurized steam. As the steam is going up, you got the pedals turning, and that's it. All right, so in that sense, we generate power exactly the same way ever since 1880s. Guys, just remember, this is a technology that's been around for a long time, 1880s. All right, so we use the Faraday's law. We just vary the flux within the loop, and that's it. We end up getting alternating current out of it. All right, so Faraday's law is generate current. We should change the magnetic flux inside the loop, and then it's going to give us
generate electric power using a lemon. When you do that, you get what's called direct current. Last time I showed you another possibility. That involved using a simple coil of wire and a magnet. When you generate power this way, the current runs back and forth or up and down, and it's called alternating current. And this is the way nearly all power, electrical power, is generated. The best way of doing it is not to move the coil back and forth, but to make it spin around steadily like that in the magnetic field. And that is the way virtually all electric power is really generated. But of course, generating the power that way requires energy to spin the coil against the magnetic forces and drive the current around. That's usually done using a heat engine, a gas turbine, which is fired by a fossil fuel like oil or coal or gas, or by a nuclear reactor, or even by water in a hydroelectric generator. I wanted to show you how to build one of these in case you're ever stranded on a desert island and have to reconstruct civilization from scratch. So I had a simple one made up for you. This is a water wheel, which goes around like that when there's water running on it. And when it goes around, it turns a coil, much like that one over there, between the poles of this permanent magnet. The electrical output of the generator comes out on that oscilloscope, which is simply a device for showing the voltage. As long as the trace on the oscilloscope is going across horizontally, nothing is happening. But when we start generating electric power, it will start going up and down like this. Okay, so when you see that going up and down, you know that we're generating electricity. And all I have to do to generate electricity is to turn on the water. All right, are you ready for this? You better get out your umbrellas in the first few rows. Here we go. And there it is, hydroelectric power.
All right, so in generating current by what means the coil or the turbine is spun? Mechanical means. All right, so what happens is through mechanical means, we end up spinning the coil or the turbine in this case, and then it changes the flux. Change of flux is what generates current. All right, so what's happening there is the mechanical energy turns into the electrical energy. So the mechanical energy of the wind, the running water, the steam will turn into electrical energy. All right, so how does spinning the coil generate electromotive force? That's the definition of Faraday's law. All right, so spinning the coil, you end up changing the flux within the coil, right? So the area exposed to the magnetic field is going to keep changing. If you change the size of the area exposed to the magnetic field by spinning it, it changes the flux. Change of flux is going to create an electromotive force, and the electromotive force is what drives current.
Before Tesla, Edison built his own generators, one after another, each more powerful than the last. But then, so had Tesla. And surely as well as Edison, he too built turbines and motors. However, and this was the big difference in the long run, Edison's generators could only illuminate things within the reach of his power plant, while Tesla's AC system could reach beyond the old neighborhood. With an ever-expanding grid of power lines, AC could go from coast to coast and just about everywhere in between.
All right, something about AC versus DC, something about Edison, and something about Tesla. And this is related to, or somewhat related to what Tesla somewhat became unknown for a while.
Obviously, the reason a plant generates electricity is to send power somewhere, to transmit it through power cables into the home, the office, or anywhere else there's a need and a handy socket. But the power is equal to the current times the voltage. Therefore, the same power can be transmitted at high current and low voltage, or low current and high voltage. Which is better? Remember, the power cables have a certain amount of resistance, and the longer the distance, the bigger the resistance, because a cable's resistance is proportional to its length. And of course, passing current through a resistance causes heating, which is equal to current squared times resistance. This is wasted heat. For the power company and the consumer, that means a certain amount of energy won't be available at the other end. Since I is P over V, that heating is P squared R over V squared. So for any given power and resistance, the higher the voltage, the less power lost in transit. In other words, the key to transmitting power efficiently is to transmit it at the highest possible voltage. In a modern electric power grid, energy is routinely transmitted over thousands of kilometers at hundreds of thousands of volts. But no matter how it's used, the recipient wants all those watts to arrive at a safe and handy voltage. And that's possible only if the electric energy can be transformed up to high voltage, which it takes to make the long trip to the consumer, and back down to low voltage for use at the end of the line. That task, raising and lowering voltage, is hard to accomplish with direct current, but with AC, it's comparatively easy.
All right, so you generate the current by using Faraday's law. All right, so you change the flux is going to induce electromotive force. The electromotive force is what drives current. And then the next question is, all right, so the transformers, what do they do? The purpose of a transformer is either, it depends if it's a step-up transformer, it's going to up the voltage for you, which means the voltage is going to go up. When the voltage goes up, the current is going to go down. If it's a step-down transformer, it's going to reduce the voltage. As a result, the current is going to go up. All right, so what's the purpose? What's the idea behind it? You got a power plant right here. You got the consumers right there. All right, if it's direct current, the distance is going to matter. All right, so this is the amount of power that you generate, and this is the amount of power which we end up losing because of resistance. And you know that the resistance of the wire is going to depend on the length of the wire. So we got a bunch of problems here. It's going to depend on the length of the wire. All right, so depending on the distance between the power plant and the consumer, larger the distance is, the larger the resistance is, and a lot of that electrical power is going to be lost in the form of heating. All right, so that becomes a huge, huge problem. All right, so a couple of solutions, obviously. If your power plant is located in Niagara Falls, and if you guys are living in Houston, in my case, Chicago, all right, so we're not going to be able to have enough current running our own business or businesses in these big cities. So it's not going to happen because a lot of that power is going to be lost in the form of heating. If you want to use direct current, there are a couple of solutions for this one. Number one, if you want to still be able to generate enough current, obviously you can make the wires really, really thick. It represents the thickness of the wires. The thicker the wires, the less power is going to be lost in the form of heating. But these wires need to be as thick as some of the big 2-3-story buildings. All right, especially if you're going to be getting your power all the way from Niagara Falls. All right, so that becomes a problem. So the solution is not economical. So no one is going to go for that. The second possible solution for this problem is you need to have a power plant at the corner of each and every single block for this to work. Once again, it's not an economical solution. So at this point, enter Tesla into the picture. So the Tesla solution is why not use a transformer? Except transformers require, all right, so the transformers will require alternate current. All right, so what does a transformer do for you? Well, what it does, it transforms current into voltage, voltage back into current, right? So you up the voltage goes up, the current is going to go down. When the current goes down, what happens to the amount of power that you're losing? It goes down as well, all right? In fact, you got these high voltage transmission lines, and the voltages are so high that you don't have a lot of current within these wires, so which means that you're not losing a lot of power or energy in the form of heating. It's not happening. So the amount of energy that you generate in transfer more or less will be the same. And then once you get near the consumers, what do? When you get near the consumers, you end up using a step-down transformer. What does a step-down transformer do? So it's just going to reduce the voltage, and that current is going to go up because the consumers want current, not voltage. Okay, guys, notice that. Remember the guy who just got shocked? All right, so he just went across a transformer just like that. He was on these power lines. They were about 10,000 to 8,000 volts, and he wasn't getting shocked. As soon as he went across, he got zapped pretty badly. All right, so transformers will require that you use alternating current.
It takes a lot to keep the electricity working, not just in machinery, but in manpower, and it costs a lot of money to maintain these systems. The utilities have to maintain their lines.
In the United States, 98% of homes and businesses receive power from a vast electrical system that is woven together with a web of power lines. A grid. These power lines are naked live wires, carrying 500,000 volts. It's up to the lineman to inspect and repair every part of the grid, usually without shutting down the power.
Yeah, Bill, I was going to start making a gradual left turn and start heading over towards the line.
One of the most daring techniques is used on very high voltage tension lines.
It's pretty dangerous, I feel, because you're mixing aviation with electricity. One, you're depending on the helicopter, everything mechanical to go right. If it goes wrong, you're going to drop out of the sky like a rock. If the lineman makes a mistake, you're going to vaporize.
These linemen and pilots work for Ag Rotors Incorporated, one of the few companies that attempts these high wire acts. Ag Rotors has the best safety record in the business.
There's linemen all over the United States that are risking their lives every day to keep the power flowing.
The dangerous marriage between helicopters and power lines is made to save money and time. Repairs that take a conventional ground crew days, Ag Rotors completes in hours.
And Bill, we're just looking for the right structure number, and then we're going to have to probably turn back a span or two once we order.
We could actually get too close to a power line and a tree, and the electricity would arc amongst all of us, and we could actually short out the power line and destroy ourselves.
If you were able to take a voltmeter, which measures voltage, and measure the voltage on that helicopter, it would be energized at 500,000 volts, and anything on that helicopter.
The metal wand gives the electricity a controlled pathway from the wire to the helicopter. Once the pathway is established, the lineman replaces the electrical connection held by the wand with metal clamps. The clamps allow the lineman to free his hands so that he can work.
I was working in the middle of the Everglades, and I knocked the bond off, unbeknown to me. And when I went to get close to the wire, the arc went straight to my mouth. So I absorbed roughly about 500,000 volts to my mouth and my nose, blew all the fillings out of my mouth, cauterized my nose, knocked me out of my seat belt up underneath the platform, the belly of the ship on the platform, and I was unconscious, it seemed like, for a pretty long time, but it was just a few seconds.
The amount of voltage may be the first fact recited when explaining the dangers of electricity. But the high voltage isn't what kills a person, it's the amps. The electricity in the lines can flow at 500,000 volts, but isn't necessarily deadly if the amps are low. Real low. It only takes 1 amp to stop the heart.
It takes a lot to
carrying 500,000 volts.
High voltage lines, 500,000. Which means that the amount of current on these lines is actually fairly small.
It's up to the lineman to inspect and repair every...
All right, the reason why this guy is not getting electrocuted is exactly the same reason that we discussed before. These are not wire mesh. Obviously, you got the Faraday's cage thing going, but that's the reason is because there's a lot of voltage there. It causes induction. It's not comfortable for the skin, so that's the reason why they wear it. Aside from that, he would be perfectly fine. All right, so The voltage difference depends on the contact points, distance between the contact points, so it's going to be fairly small. So which means that the current between the contact points is going to be fairly small. His body becomes parallel to the wire, so once again, body offers a lot of resistance, is going to be fine. Okay, now we got problems. These lines are at 500,000 volts. Chopper is not. Okay, so if there's a potential difference, there's going to be current. All right, so you could get yourself potentially killed. So what he's using this metal wand, and then he's just noticed that what's happening is the charges are jumping from high voltage towards the low voltage. Eventually, the voltage difference is going to be 0. All right, so everything becomes an equal potential surface at this point. If there's no voltage difference, you're perfectly safe. These guys are inside the chopper, so it's a metallic enclosure. Those guys are just fine under the circumstances. Everything is fine. All right, so a couple of things that they do, which is real impressive, and it's applied physics. All right, so when they're near these high voltage lines, okay, so this is 500,000, this is not. So there's going to be a huge voltage difference and potential difference. This is actually holding out to the metal wand. And now the current is given a choice. Obviously, this is metal. It could potentially go through your body, but it's not going through the body because the body offers a lot of resistance. So it's just going to the chopper. It's going to remain outside of the chopper, so he's going to be fine. And then what they need to do is, as soon as they equalize the voltage or potential difference, they're going to end up using clamps. All right, so they will have 2 clamps. So everything is part of the circuit. Instead of using a single clamp, obviously, it's the redundancy under the circumstances. You have to be redundant. If you knock one of them off, the second one is still connected, so there's no voltage or potential difference. If you knock both of them off, then if the current doesn't have a path to go through, it's going to go through your body, and then you can get yourself
to free his hand
it gets real dangerous.
so that he can work.
I was working in the middle of the Everglades, and I knocked the bond off, unbeknown to me. And when I went to get close to the wire, the arc went straight to my mouth. So I absorbed roughly about 500,000 volts to my mouth and my nose, blew all the fillings out of my mouth, cauterized my nose, knocked me out of my seatbelt up underneath the platform, the belly of the ship.
Okay, so he thinks that it's 500,000 volts. No, the voltage difference is the voltage difference between the chopper and then these lines. It's not going to be 500,000 volts. It's going to be pretty close, or else he would not be alive. He wouldn't be talking about it.
It started with the best of intentions, and then everything went wrong. A cat had gotten caught on a utility pole, and after neighbors failed to talk it down...
All right, so the problem with the utility pole is obviously one line is going to be at a higher voltage than the other one. All right, with the utility poles, you have transformers on top.
The firefighters reached out to grab the recalcitrant feline. "15 minutes passed, and a man's life hung in the balance. And then he regained consciousness, suffering from severe burns to the hand. Amazingly, the cat survived without injury, and was last seen running from the scene 8 of his 9 lives shorter."
I'm actually impressed that this guy decided to go up to grab the cat. Most firefighters would not do that. This sort of stuff is dangerous, obviously, and here's the reason why. You got a transformer there. The cat, you will spook the cat. What do you think is going to happen? All right, so he got zapped pretty badly. The cat survives. That's physics when we discuss that. Notice what happens to his body. His body lights up. His butt just lights up more because that's where the fat is. And then he gets zapped again. At the end, all is good. He survives, so things work. All right, so the next question is, transformers, how do they work? All right, so here's the setup for our transformer. All right, so let's study that carefully. Okay, so transformers will have two coils. One is called the primary coil, which is located right here, and you got your secondary coil. And then you got an iron core connecting these two coils to each other, in essence. All right, so the primary coil is connected to an AC generator. So what does the AC generator do? It generates an alternating current. So the current is going to go this way, and then it's going to reverse direction, and then go forward, backward, and backward. All right, so not only current is going to keep reversing direction, also the value of the current is going to keep changing. It's going to increase and decrease, so that's what happens. All right, so you reverse the direction of the current as well as the value of the current. All right, so notice that this is a primary coil. There's a coil here. It's got a number of turns, and then the current goes this way and that way. And the current itself generates magnetism, right? So the current goes this way, the magnetic field is going to go that way. And then current reverses direction, the magnetic field is going to reverse direction. And then we have this iron core, something about iron that we know, it becomes easily magnetizable. It becomes easily magnetized, in essence. It's magnetizable. It becomes easily magnetized. All right, so the current goes this way. It's magnetized. Everything is magnetized in this direction. It reverses the direction of the current. So the polarity of the magnetism is going to become reversed. It reverses the polarity of the magnetism. All right, so when the core becomes magnetized, the entire iron core becomes magnetized. It's going to become magnetized this way, and then it's going to become magnetized that way. Notice that within the iron core, we end up changing the strength of the magnetic field, as well as the direction of the magnetic field, at will, by reversing the direction of strength and the direction of the current within the primary core. So the magnetic field, strength of the magnetic field is going to increase in this direction, and then it's going to diminish in the opposite direction, and then the magnetic field is going to reverse direction, and so forth. Notice that the magnetic field within the iron core is intercepted by the secondary core. So in essence, every time we change the strength of the magnetic field within the iron core, we end up changing the strength of the magnetic field in the secondary core. So what does that do? Well, if you vary the strength of the magnetic field within the secondary core, what do you think is going to happen? It's going to generate current in the secondary core. So the alternating current within the primary coil is going to end up generating an alternating current within the secondary core. All right. And because we end up using an iron core to contain the strength of the magnetic field. So you vary the strength of the magnetic field within the iron core, whatever the variation here is going to be the same variation over there. All right, so how do we turn this into a device that's going to increase the voltage in the secondary and reduce the current in the secondary? How do we turn this into a device that's going to reduce the voltage in the secondary, thereby increase the current in the secondary? How does that happen?
If alternating current passes through a loop or coil, it produces a constantly changing magnetic flux. A bar of iron, magnetized by the coil, can concentrate and intensify the changing flux. In fact, an iron ring can contain the flux entirely. And if a secondary circuit is wound around the ring, as the changing flux passes through it, a voltage is induced in it. That voltage is proportional to the number of turns around the iron. Obviously then, the voltage of the power transmitted to the secondary circuit can be made higher or lower than the voltage in the primary circuit. So although the power out is nearly equal to the power in, it can be stepped up to high voltage for long-range transmission, and then brought down to low voltage for safe use at the end of the line. It's exactly this principle which is the greatest advantage of Tesla's AC over Edison's DC. And while it was revolutionary at the end of the 19th century, that principle would be applied from one end of the earth to the other in the 20th. That fact, the overwhelming evidence that alternating current powers the modern industrial world, makes the case for declaring Tesla the winner in the war of the current.
Wow, I didn't realize there was a war going on, and Tesla is the winner.
If alternating current passes through a loop or coil.
All right, so keep reversing the direction of the current. So what happens? You end up reversing not only the strength of the magnetic field, but also the direction of the magnetic field, right? So the current goes one way, the magnetic field is pointing in the downward direction, and then you reverse the direction of the current. The magnetic field is not pointing in the opposite direction, and its strength is increasing. Its strength is increasing. So scope. Sometimes the power point does that. Okay, so what happens if you place an iron core in the middle? So iron is going to become magnetized. And then by reversing the direction of the current, you will reverse the direction of the magnetization. So you end up changing the polarization of it. All right, so you keep reversing polarization. So the faster you reverse the direction of the current, the faster you will change the direction of the magnetization of it. All right, so if you have an iron core, if you just had a loop iron core, just like that, when you vary the direction of the current as well as the magnitude of the current, you're going to end up reversing the strength as well as the direction of the magnetic field within the core. Notice that strength and the direction of the magnetic field changes uniformly within the core. The nice thing about the iron core is it's going to contain the magnetic field within it. So you have complete control over what's going on. So you're varying the strength as well as the direction of the magnetic field inside the core. And you're also controlling how fast you're changing the strength as well as the direction of the magnetic field within the core. And then you place a secondary loop right here. So as you're changing the flux here, obviously changing the strength as well as the direction of the magnetic field here, you're changing the flux, you're changing the strength of the direction of the magnetic field by the same amount here. So the amount of change in flux here is going to be the same as the change in flux there. And change in flux is what induces voltage, in essence, on the secondary core. All right, so the question is, how do we increase the voltage on the secondary, or how do we reduce the voltage in the secondary? How does the magic happen? Okay, guys, voltage on the secondary compared to the voltage in the primary. Okay, the whole idea of this is, if it's a step-up transformer, it's going to up the voltage. What that means is you're going to increase the voltage. If it's a step-down transformer, it's going to reduce the voltage. That's what it means. So how do you increase the voltage, and how do you reduce the voltage? You increase the voltage goes up, the current goes down. You reduce the voltage goes down, obviously the current goes up in the secondary. So that's what we're trying to do. Well, it depends on the number of turns in the primary versus the number of turns in the secondary. We got the number of turns in the primary, current is going this way and that way. Obviously, it generates a magnetic field, and the magnetic field is going to be contained within the iron core that you're looking at. So if you change the strength of the, if you change the strength as well as the direction of the current, it's going to change the strength as well as the direction of the magnetic field within the core itself. And that variation within the strength of the, as well as the direction of the magnetic field within the secondary loop is going to generate an electromotive force in the secondary loop. All right, so the question becomes, how do we control the voltage in the secondary? How do we generate the voltage within the secondary? Okay, I'm changing the flux within the primary. Changing flux within the primary, which is here, is going to be the same as the change of flux within the secondary. Okay, so the variation of the strength as well as the direction of the magnetic field within the secondary is going to be the same as the variation of the flux within the primary that you're looking at. Okay, so changing flux within the primary is going to generate an electromotive force or voltage within the primary, and change of flux within the secondary is going to generate an electromotive force or voltage in the secondary, right? The voltage in the primary and the voltage in the secondary depend on the number of turns, according to Faraday's law. All right, so the voltage, both of them will experience the same change in flux. The voltage in the primary depends on the number of turns in the primary. The voltage in the secondary is going to depend on the number of turns in the secondary. If I were to increase the number of turns in the secondary and make it more than the number of turns in the primary, it's going to give me a higher voltage in the secondary. That's it. It's Faraday's law, in essence. If I were to increase the number of turns in the secondary, it's going to increase the voltage in the secondary. And the voltage is going to go up, the current is going to go down in the secondary because it's related to power at that point. All right, so the change in flux within the primary as well as the secondary is the same. That's the strength of the magnetic field intercepted by both areas will be the same, or the variation of the magnetic field intercepted by both areas will be the same. So change of flux is going to be the same on both of them, so which means that the electromotive force is only going to depend on the number of turns. All right, so the electromotive force is going to depend on the number of turns. So if you increase the number of turns in the secondary, it's going to increase the voltage in the secondary, and then the current is going to go down in the secondary. You reduce the number of turns in the secondary, the voltage in the secondary is going to go down. The current in the secondary is going to go up. All right, so if it's a step-up transformer, in the secondary, it's got the larger number of turns. So the number of turns in the secondary is going to be more than the number of turns in the primary. If it's a step-down transformer, the number of turns in the secondary is going to be less than the number of turns in the primary. All right, so this was the suggestion that Tesla came up with. He said, let's use transformers. Let's use transformers. That's it. All right. So you increase the number of turns in the secondary. So what happens? The voltage in the secondary goes up. The current in the secondary goes down. So you don't lose a lot of power in the form of unity. Edison, being a genius that he was, he said no. He said, no, we're not going to use transformers. We're not going to use AC current. I mean, hopefully you guys have an understanding of what Tesla was talking about. And Edison is supposed to know his stuff. How come he missed the point? I got news for you guys. He didn't miss the point. He knew exactly what Tesla was talking about. He said no because AC is dangerous. Alternating current is dangerous, especially high voltage alternating current. We discussed that before. He was afraid that people were going to get themselves electrocuted. People were going to die. He thought that there was going to be a mass panic. And he thought that he was going to lose his business. He didn't want to take a chance with that. The alternating current, I mean, you come in contact with alternating current, what happens? They keep changing direction like 60 times per second. The muscles are electrical organs. When you become part of a circuit, if you touch it with the inside of your palm, your hand is going to get paralyzed around it. And if you remain part of that circuit, sooner or later, it can kill you. That sort of stuff is really dangerous. Edison didn't want to take a risk on that. He said, no, let's not do that. He said, let's use direct current. He didn't know how to solve the direct current problem, but this is what he wanted to do, in essence. And he was the only person in that business, in terms of the electrical distribution system business, obviously. Not for long, though. He and Tesla didn't get along. Okay, these two didn't get along. Tesla quit. And someone like Tesla today, exceptional talent, if he were to quit a job like that, he would get a better one, but tons more money. Except the problem was he thought that he was going to quit and he was going to start his own business. Things didn't work out that well because Edison at the time did not have main competitors. All right, and then we had some problems.
To other industrialists. He had created a new market as vast as America. To competitors, it was irresistible, and in Pittsburgh, the giant Westinghouse industrial empire began to investigate the market for electricity. In 1882, George Westinghouse was at the peak of his powers. He had made his fortune in railway equipment. He saw his future in electricity. He set out to challenge Edison's electrical dominance, combining ingenuity with industrial might.
During Westinghouse's lifetime, he started 60 companies, but he had 50,000 employees, which was by far the biggest employment workforce of anyone up until that time. He was one of the first visitors to come and admire the Edison system. But it's in the nature of any industrialist and inventor to basically, number one, find out what other people are doing, but then next, how can I do it better?
Edison used direct current. Rotating magnets generated the electricity, but the fluctuations were evened out to produce a one-way current. The system worked best at low voltages with short transmission runs. Edison's vision was of a DC generating station on every street corner in built-up areas.
Direct current had its limitations. Couldn't be transported over great distances. You needed very large copper wires to do that. So you have a copper wire. To go a mile, you need a copper wire the size of a man's leg.
Westinghouse pioneered a system which could travel over thin and cheap copper wires. It also used revolving magnets, but used the rapid fluctuation in polarity to create an alternating current. He built transformers which wound the current up to high voltage, making it lethal. The Westinghouse system had positive advantages over direct current, and he invested massively in AC.
George Westinghouse was a brilliant inventor. He very quickly grasped the significance that with alternating current, you could transmit the power over a very long distance. And so you didn't have to have a power station in everybody's backyard, as you did with direct current.
Edison's system was crippled by its generating and distribution costs. The thick copper cabling it needed made it uneconomic, and the direct current system began to falter. Westinghouse, the admirer of Edison, was increasingly confident of the superiority of his own system.
Westinghouse started to cut into the business and became a very serious competitor. And even after just 2 years, he was outselling Edison in new installations.
Edison, the electrical pioneer, was challenged and affronted. His will was total, and the contest was underway to put electricity to its darkest use.
Well, Edison was wrong. He was feeling fairly safe. He wanted to use AC current. He wanted to use DC current. The problem with DC current is transmission. It became really costly to transmit current. And then Westinghouse, this guy was originally was an engineer, so he sees the potential. All of a sudden, he and his team of engineers noticed that AC is the way to go. And they noticed that they could use transformers and be able to transmit current cheaply. All right, and then they started looking for patents. And then evidently, Tesla had his patents already, his stuff already patented, and they found his patents, Tesla's patents. They wanted to buy the patents from Tesla, so they started searching for this poor guy, and evidently Tesla, right after he quit, he couldn't get a job because Edison Company was the only company in the market at the time. And he thought that he was going to be able to find some people who could just give him money so he could start his own business. He was looking for investors. People didn't know him, so there were no investments. And all of a sudden, he ran out of money. All right, life wasn't comfortable, so he ended up working for the city of New York, digging ditches for the Edison Company, because Edison decided that he was going to run his power lines underground. And they needed people who could dig ditches. And next thing you know, that's exactly what Tesla was doing. I mean, he was almost suicidal. This guy was depressed. He was suicidal. And then the Westinghouse Company is interested in his patents. He said, okay, I'll sell you the patents. That's fine. It wasn't a big deal. And the problem with Tesla is, and that's still a problem with most of his patents, it's always the same problem. This guy would have these ideas and insights, the visions of what was supposed to happen. These things would just pop into his head ever since he was 14 or 16 or whatever. And then he would just design them. And then he would apply it for a patent without building it, because he didn't have the money to build most of what he was imagining. All right, so Westinghouse buys his patents, except they're not working. Obviously, they're not working because they haven't been tested. So they go back to him and they say, would you want to work for us? He said, okay, I'll work for you. And he had a bunch of conditions. Obviously, he wanted to have his own private laboratory, which they gave him a private laboratory. On top of that, he ended up getting a cut on the earnings. The guy was a millionaire at some point. He was making tons of money working for Westinghouse Company. Now the Edison started to lose his market share because direct current is not as efficient. It's much more expensive. Blah, blah. So what do? The Edison's biggest fear was, AC is dangerous. He thought that there was going to be a mass panic. It was wrong. He was wrong. I mean, people were getting killed. There was no question about it. He was right. AC is more dangerous, and people were getting killed. There were accidental electrocutions all over the place, but most people didn't care. It's just general apathy. All right, as long as it's not happening to you, you're fine. All right, you're not going to worry about it. If somebody else's kid gets killed or wife gets killed or whatever, all right, so that's not your problem. And people were happy that they were getting electricity cheap, so Westinghouse was winning the market. All right, so at that point, Edison is thinking, oh, people just don't understand how dangerous it is. So they started to do some public shows, I'm going to say, executing dogs, cats. I don't know, they end up executing an elephant using electricity. And then all of a sudden, the idea occurred to him that they could probably do a better job by coming up with a way of executing people. All right, so the idea of electric chair was born out of that. So the next thing is you have to sell the idea to the state. This is the state of New York. So they hire best of the best attorneys. They argued that, hey, in terms of the firing squads, obviously that's too military. Hanging is too British. And guillotine, obviously out of the question, it's too French. So the best way to execute is electric chair, the modern way, because the United States is the leader of technology. So why not do it the American way? They pushed for that. Eventually, they convinced the lawmakers that the executions could be carried out without causing any undue pain or suffering. And you guys saw what happened during the previous week. They got a volunteer and they sold the idea to him. They said, hey, it was going to be done quickly. There's not going to be any pain. Don't worry about it. Except the execution just lingered, right? Things didn't work out as planned. Now, for the first execution, Edison and his team decided to get a Westinghouse power generator. The whole idea is use an alternating current and demonstrate that alternating current is dangerous. The electric chair works on alternating current. And if you're going to be using alternating current, you might as well just hit the competition, right? Just get a Westinghouse alternating current generator and coin the term Westinghousing someone. It's not, the whole idea was to coin the term Westinghousing someone, all right? So that people would know that the Westinghouse, the current that they were getting was dangerous. Westinghouse company, realizing what Edison and his team was up to, they decided not to sell a Westinghouse power generator to New York State. As a result, Edison and his team, more like his team, decided to go to one of the South American countries and get a Westinghouse generator from outside of the United States for the first execution. We still have the electric chair, obviously, most states do. And the term Westinghousing someone did not catch on. It didn't catch on. And the battle between AC and DC, obviously AC ended up winning. We have AC distribution systems. DC is expected, was proven to be way too expensive. Eventually, Edison was forced out of his company, all right? So the board of directors ended up removing him.
One of the questions that came up, and one of the big advantages of DC, direct current, was that it was safer. It traveled at lower voltages and was perceived as not being as deadly. When Edison began to kind of lose the marketing war with Westinghouse, he started to look at and focus on his main advantage, and that was safety.
Edison seized upon the new battleground, and his organization started to pump out stories trumpeting the lethality of high-voltage alternating current. Edison was fighting back, associating Westinghouse's AC current with the fear and mystery of death by electrocution.
They had no concept at all of electrocution. Some thought it might be its effect on the brain, on the spinal column. They just had no idea. They have cases like in Buffalo, New York, where a man went into a generating station when he was drunk, and he put his fingers across the generator and got a shock, and he died relatively quickly. And thought, gee, isn't that a nice way to kill criminals? Because look how quickly the man died.
All right, the correct answer is not, he did not like Tesla, obviously. These two didn't get along. They were not big fans of each other. Obviously, Edison blamed Tesla for losing a big share of his business. He knew that Tesla was working for Westinghouse, but that's not the reason why. All right, the reason why he was against alternating current, because the high voltages required could be deadly. All right, so he didn't want to take a chance on that one. He did it on business reasons.
Tesla was certainly a genius of the first magnitude.
So what happened to Tesla? Why is it it was almost forgotten by the time he passed away?
If Michael Faraday could imagine space filled with lines of constant force, Nikola Tesla could picture multi-phase generators and multi-phase motors all connected with complex electrical circuits, and when they were built, all of it would work perfectly, exactly as he had imagined it. Time and again, Tesla made fortunes and squandered them, but turned down soft jobs with fat salaries just so he could be left alone to think and to invent. You might say that Tesla, like Da Vinci before him, was a true saint of engineering. He died almost forgotten and almost penniless in New York City. But it was Nikola Tesla, at least as much as Thomas Edison, who shaped the nature of the world that we live in today.
Part of the reason why he was almost forgotten is because Edison, over the publications that he had control, decided to have Tesla's name suppressed, at least according to one of the books that I was reading. The title of the book is Einstein's Fridge. All right, so there's a bit of a claim regarding that. The reality of it is Tesla didn't do a lot of publications. He would come up with these ideas. And these are the things that would just pop into his head. Like I said, he would design them and then apply for a patent. If he had the money, he would build them. And according to him, everything would work exactly the way he envisioned it in his head. There's no publication. So without publications, you would have a hard time getting credit for that sort of stuff. And I think part of it was his personality. All right, this guy was
no one since Ben.
He was a savant. He didn't have the. I don't think he quite had the personal skills to actually defend his own path.
Franklin had gone as far as Thomas Edison, but in his own way, Nikola Tesla would go even farther. Long before they became a reality, Tesla had envisioned vacuum tubes coated with phosphor and glass tubes filled with gas, fluorescent lights, and neon lights. And years before the Wright brothers appeared, Tesla claimed that if aviation were to get off the ground, it would need to use a then almost unknown metal called aluminum. And while Guglielmo Marconi got the acclaim of the popular press for inventing the radio, Nikola Tesla got the credit, as well as the final verdict in the courts. Speaking of credit.
So Marconi gets the Nobel Prize for it. He also gets the credit for it. Eventually, they end up suing Marconi because Tesla has the original patent on it. And then the case goes all the way up to the Supreme Court, and the Supreme Court awards him with the original patent at the end. So the decision was reversed. Of course, he didn't get the Nobel Prize for it. And besides, he wasn't the one who did the suing. The people end up suing on behalf of Tesla. His friends did. And they end up suing Marconi shortly before Tesla passed away, so that he would get the recognition and honor.
Some state that Tesla was denied his due for many original inventions. In all, no one can deny that Tesla was one of the most dynamic scientists who ever lived, nor that his mind was fertile and inventive beyond compare. But Tesla, more interested in invention than in scientific publications, kept much of his methodology in his head.
Yeah, he didn't publish it.
Perhaps that's why the scientific community remained dubious or miserly with its praise for years. He did, however, receive honorary doctorates from Columbia and Yale. And in the end, with unintended irony, Nikola Tesla was even honored with the Edison Medal, that most prestigious award named for none other than Thomas Edison himself.
Edison Medal is the same as Nobel Prize in Physics. Edison Medal in Engineering is the same as Nobel Prize in Physics. He was awarded the Edison Medal towards the end of his life. That's kind of ironic.
The man who
And he was poor and penniless at the time.
made possible most of our modern uses of electricity. Thomas Edison?
It's ironic because these two don't like each other.
No, it's Nikola Tesla at number 7.
Nikola Tesla is one of the most wildly inventive minds that the world has ever seen. He was hugely influential, to say the least, in creating alternating current and thereby setting a standard for all of the electrical power grid that we know today.
Nikola Tesla started working in 1882 at the Paris Edison company. He tried to promote his idea of using alternating current. They were not particularly interested, and so he decided to go off to the United States and talk to the man, Thomas Edison himself.
He was given a letter in introduction to Edison. In fact, the letter said that there are two great electrical geniuses. You, Mr. Edison, are one, and the gentleman standing before you is the other.
But they very soon had some severe fallings out, in no small part over the issue of AC versus DC current. Tesla very strongly supported AC. Edison had a lot of financial investment in DC, and they simply could never reconcile those problems.
Often a stubborn and unyielding taskmaster, Thomas Edison pushed Tesla to work on the company's direct current generators by promising Tesla a financial incentive.
He said, if you could solve these problems, I'll give you $50,000. Tesla worked like a dog for months, corrected all the problems, brought the solutions to Edison and said, yes, thank you. Now, where is my $50,000? And Edison is supposed to have said, well, my dear Mr. Tesla, you don't understand the American sense of humor.
Edison's harsh demands and empty promises crushed Tesla, driving him to quit the company. Without work or money, Tesla became despondent, almost suicidal. At the last minute, a Westinghouse manager offered him his own lab. Finally, Tesla was able to realize his vision and was vindicated.
There was a competition between Edison Company and Westinghouse for the building of the City of Lights at the 1893 Chicago World's Fair. The cost of distributing power through alternating current was basically half of the cost that was proposed by Edison. So Westinghouse won the contract, they built the City of Lights, and it was a clear demonstration of the tremendous advantage of AC over DC.
His victory with alternating current was a turning point. It opened the door for Tesla to advance radio, remote control, and a host of other technologies ranging from radar to neon lights, earning him over 700 patents and securing his place in history.